Hello and welcome to my channel. So in this session we are going to see assembly language program to count the number of ones and zeros in two consecutive memory locations. So let me give you a brief introduction how to write an assembly language program in a Keel Microvision 4 editor. Okay. So first of all, to create a project, we need to click on the project here in a menu bar and click on new Microvision project. Okay, once you do that, it will ask you to create a project file. Okay, so you can create your own folder here. Let me create a folder here in any workspace. Okay, create a folder here, new folder. I'll write test project. Okay, test project, and you can give the name of that particular project. In that particular folder, I'm giving the name. Okay, I will give it as test. And you can see the extension of the project file will be .uvproc. Okay, Microvision project. Save it. Once you save it, it will ask you for the selection of the microcontroller. Here you have to go for this NXP founded by Philips, and here we have to check for LPC2148, because for all the programs we are writing an assembly language program for LPC2148 based on ARM7 cores. Okay, based on ARM7 core. So we have to select LPC2148, search for that LPC2148 here. You can find it here, and you can see the description here. It is an ARM7 TDMIS based high performance 32-bit. See, all the registers are 32-bit. Of course, the ALU, everything is 32-bit here, and it is a RISC microcontroller, reduced instruction set computer. Okay, RISC microcontroller with the thumb extension, 512 KB on chip, flash ROM with the ISP, that is in system programming and in application programming, 32 KB RAM. We have 32 kilobyte of RAM. Okay, it is a vectored interrupt control, and there are several other information which is related to LPC2148. Now once you select that LPC2148, you have to click on OK. Okay, as you can see here, I had already selected it, right? Okay, click on OK. Okay, then it will ask for this prompt: copy Philips LPC2100 startup code to project folders and add file to project. For all the software projects, you can click no. For all the hardware projects, okay, we have to click on yes. We require the startup.s project folder. But as of now, I'm clicking on no. Once you do that, you can see one target folder got created here, and in that you can see also there is a source group 1. So this is the group in which we need to add up our ASM file, that is an assembly file here. Okay, now once you get this, we have to click on here file new or create an empty document here. Okay, now I'm going to write one small program for data transfer instructions. So as you can see here, I had written one small program for data transfer operations here. Okay, so once I write this program, you need to save this program. Okay, you can click here save the program and save it in the same folder in which you have created your project file, that is a test project folder, and here you can name the name of your program. Okay, I will write it as test itself, test.asm. This is an assembly program. .asm is extension for every assembly language program. Save it. So once you save it, you can see everything. There are some colors and all it has come because it indicates various types of data here. So all this these are the data hash, whatever you give, R3, R1, these are all the registers. Okay, now let me explain you this program. So this program is a very simple program to show you the demonstration of all the data transfer operations here. So you can see TTL, this is an assembler directive, and this is nothing but the name of your program, and this is the code segment area. Okay, the name of the area is proc. Okay, and this is a code segment and it is mapped to read only. This is an entry point in which we are going to write the logic of the code, right? And this is the start and stop labels, which is left justified, and the logic of the code we are writing towards the right. At least one tab space has to be given here. Okay, now, and you can see there are I am using R0, R1, R2, R3, 4 registers I am using just for the demonstration purpose. Here you can see the value of 1 is added to is moved to the R0, and you can see the hexadecimal value. Whatever the number you write with 0x, it is nothing but a hexadecimal, and when it gets stored in R1, it is showing you the 32-bit value. Okay, because all the registers in ARM7 are of 32-bit numbers. Okay, similarly, when you store the data, it is going to, what does R2 will store? R2 is not going to store 21. R2 is going to store the hexadecimal of 21, and the hexadecimal of 21 is a 15. Okay, because 16 ones are 16, what is the remainder is 5, so 1 and 5, 1 5 will be stored. So it will store it in 0x00000015. Okay, and if you want to copy the register from one data from one register to another register, you can use these operations and all. Okay, and this is to load and store the data, because only two operations is involved in the memory, that is to load and store. Load is to load the data from the memory to the register, and store is to store the data from the register to the memory. Okay, it's a simple program. However, in the future sessions, I'm going to explain you each and every single instructions. Okay, anyways, so once you write this program, you have to click on this target folder, double click on the source group 1. It will ask you for the assembly file here. Check for the files of type, select ASM file here. Okay, once you select ASM source file here, click on that particular file, test.asm, click on add. Once you click on add, close. Okay, and please verify that it has been added to the group successfully or not. That is test.asm. Once it is added, now it's time to compile the program. Okay, compile the program. Here you can translate it. You can see there are 0 errors and 0 warnings, and then you have to click on this build. Okay, once you have built the program, you have to click on debug. This is a debugging session, and when you click on this debug, click on OK here. You can see several windows. There are register windows, disassembly window, text editor window, command window, and there is a memory window also. Okay, and if you want to see the memory, you can click on here, memory 1. Okay, watch 1, UART cables and UART serial windows also, you can see it here. And to see that, you can click on view here. Okay, if the memory window is not coming, you can click on view, and you can see there are several windows, whichever you would like to have it. All the UART windows, you can see it in the serial windows. Memory windows, you can see it here, memory 1, 2, 3 and 4. Like to see the outputs and all, you can make use of these options here. Okay, and if you want to increase the font of this program, you can directly go to edit, go to configuration. Okay, in the configuration, you have to go to this colors and font, and click on this ARM editor ASM files, and click on this Korean new. Okay, and here you can increase the size of the program. Click on OK. Okay, and you can see that there is a change in the size of the font size of the program. Now to trace the program, we can just see some options here. Okay, you can see step F11 or F10. Okay, now to go for a single step line by line execution, you can see it here. You can go through here, move R0, 1, and you can see the results here. See here, look at here, R1 0x21. Okay, now you see what is the value stored in R2. It is 15. Hexadecimal of 21 is 15. R3 will store the same value as that of R1, R0. Okay, and you're loading and storing. Okay, that is going to use some of the registers. So when you use the LDR R0, R1, that means you're loading the data from the memory to the register. So you're loading the data, okay, in the which is pointed by R1, the content of that R1. Content of R1 will have the data, and that data is stored in memory, that you're going to load it in a register R0. Similarly, R0 data, you can also send it back to the memory using STR, okay, instructions. So this is how we are going to debug the programs here. Fine. Okay, now let us proceed with the program. So let us write the assembly language program to count the number of ones and zeros in a given number. Okay, so before I write the logic of the program, let me explain you the numbers which I am going to take it in this program. The numbers are 0x01. So this is nothing but an 8-bit number, okay, or a byte, 1 byte number, okay, 8-bit number. Only two numbers are there, you can see. This is a hexadecimal number, of course, okay, and the second 8-bit number is 0f. So when you use 0, 1 and 0f in hexadecimal, so in a binary format, let me show you, you are going to write it in this way. 0 0 0 0. Okay, so it should be 8-bit, no? 0 0 0 1. So this is the binary format of 0x01. Okay, because you are storing it in DCB means what? Defined constant byte. That means you are going to take only 8-bit of data from the memory, right? And how are you going to store? What is the binary format of 0f? It is 0 0 0 0 0 0 1 1 1 1. So in this way it is going to store. Okay, 1 1 1 1 1 1 1 1 means f. Okay, so this is 0 1. This one is 0 f. 0 f. Now you should count the number of zeros in both the numbers. How many are there? You see 1 2 3 4 5 6 7 8 9 10 11. So there are 11 zeros. 11 zeros means in hexadecimal how will you write? In hexadecimal you write it as B, because you know 0 1 2 3 4 5 6 7 8 9 A B C. A means 10, B means 11. So there are 0B or 11 zeros, and how many ones are there? 1 1, count it, 1 2 3 4 5. So there are 5. So there are 5 ones are there. So this should be the output. My output should be 0B and 05 for this number 0x01 and 0x05. Okay, now to display this number, this has to be stored either in a register or in a memory. Now let us see how we are going to calculate this, how we are going to write a program so that the processor will count this number of zeros and the number of ones in a given two 8-bit numbers. Okay, now to do that, special assembly directives we may require it, and special logic also we may need to apply it here. So what is that logic we are going to see in this program? So let us start the program. I hope you understood this. Okay, yeah. Now this is the data segment memory. Okay, this is a data segment and the name of the data segment is SRC. Okay, and it is in read only memory. Okay, so it is again mapped to read only. And there are only two values here of type DCB, 0x01 and 0x0f. Okay, there is one more area, that is DST, destination. Okay, there are two data segment area here, and this is read write. This is read write. Okay, so here in this read write I have two labels or two variables, ones and zeros, wherein ones and zeros both have been initialized to 0 at a very initial stage, because this is the one which is going to show you the number of ones and zeros. That is, this is going to show you 5 and this is going to show you B, right? So the final answer I need to display it in these two memory locations. Okay, and you can see the type is given as DCB, defined constant byte, because of course the numbers whatever you get it as an answer will also be in terms of byte. Okay, so I hope all of you are clear till here. Right, now we will go to the logic of the program. The first assembly directive is TTL. It represents the title of the program, number of ones and zeros. Okay, this is the area. Okay, and the name of the code segment is program 8 and it is mapped to read only. Now this is the entry point in which we are going to start with the logic of the program. And towards left you can see all the labels here: start, up, top, increment 0, down, stop. Okay, so this is the these are all the left justified labels, and the logic of the program we are writing at least one tab space towards the right. Okay, remember one thing, when we expect computer to give us the output, we have to write the instructions in a particular order. Now the thing is, we need to come to a conclusion how the computer is going to count the number of zeros and ones. Okay, zeros, how it is going to count the number of zeros and ones, what and all we need to do. Whenever it encounters with 0, okay, there is a flag called 0 flag. Okay, 0 flag, and that has to be set to 1. When the 0 flag is set to 1, so this is the logic I'm using in very simple language I'm explaining you. Okay, whenever the 0 flag is set to 1, that means there is a 0 in that particular bit. Okay, there is a 0 in that particular bit, and automatically please increment the counter by 1, saying that okay, I got the first 0.
when it searches for the second bit, again if the 0 flag is set to 1, again increment the counter by 1. So that means I got the second 0. In that fashion I keep on adding so that I get the final result. Okay, similarly the same case with respect to the number of ones. This is the very simple logic we are using. Okay, now let us see one by one how we are going to write it. The code seems to be lengthy, but actually the logic is very simple. Now what we need to do, we need to load the address of SRC in R0. Okay, you can see here what is there in our SRC. Yeah, this one, right? We want the first value. What is the first value we have? What is the first value we have? This one, 0 1, and 0 1 is represented in this particular fashion, binary format. Okay, now to get that 0 1 I need to have the address. Okay, now nobody knows the address of the memory. There are billions and trillions of locations. Again, memory, remembering all the memory address is not that easy. Okay, and it's impossible to. Okay, now how can I know the address of that particular memory? By writing equal to. Okay, equal to SRC. If you write now, you will get the base address of SRC. That means base address of this memory location. In that base address, what is the value stored? 0x01. Okay, now what I need to do, you see here, I just use exclusive OR, logical exclusive OR for R5 with the same R5. Okay, now why do I need to do this job? To make R5 and R6 as 0, because initially I want all the bits to be 0. Okay, that's the reason, because R5 and R6 I'm going to use an exclusive OR. You can also initialize the value R5 and R6 with a 0, but this is another way to do that. Any number, if you're going to apply the logical exclusive OR with the same number, then the value will become 0 here. Okay, so we are writing it R5 exclusive OR with R5 and store the result in R5. This is a triadic instructions here. Similarly, we are going to do it in R6. Now here R6 or R5, sorry, let me tell you the first number. R5 is going to hold the number of zeros. Please make a note. R5 is going to hold the number of zeros and R6 is going to hold the number of ones. So in R5 I will get the final answer, R6 I am going to get the final answer, and that I am going to store it in a memory by the name ones and 0. That's the logic. Okay, so to make it a 0 I am applied here exclusive logical OR. Okay, you can apply some other assembly directive also, that is up to you, up to the programmer. Okay, now here, now I am moving the value 2 to R2 and 8 to R1. Now what is the necessity of doing this? Why I had assigned the value 2 to R2? Because I have only 2 numbers. If there are 3 numbers, then assign 3 to R2. That's all. Because now when I explained you earlier that how many zeros are there, I counted for both the numbers, right? 1 2 3 4 5 6 7 8 9 10 11. I counted for both the numbers. Now I need to know both the numbers, I need to consider. That's why I assigned 2 to R2. And in each number there are 8 bits. See, for example, in 0 1, if you want to represent it, there are 8 bits because you are told DCB, right? 8 bits are there. 1 2 3 4 5 6 7 8. 8 bits are there. When it is 8 bit, then means I need to check each and every bit and ensure myself whether that number is 1 or 0. Then only I will be able to count it. That's the reason that 8 is assigned to the value to the register R1 here. Okay, and once you're clear till here, now what I'm going to do, I'm going to load. As I told you earlier in my all the other sessions, that 2 operations are involved in the memory, that is load and store. Load is to load the data from the memory to the register, and store is to store the data from the register to the memory. Okay, now what I need to do, I need to load that value, which is the first value, 0x01. Okay, and to load that, I need to have an address. Address I had already taken here. See, address I had already taken. Now if I give you the address, how can you access the data? Yes, absolutely, I can access the data. How do I access the data? If they put that R0 in the content, put it in square brackets. If you do that, now you are going to load the data which is pointed by R0 to the R3. Done. And you are writing LDRB here. Remember this, LDRB if you write means it is loading only 1 byte of data, that is 8 bits. Okay, after that, now I'll show you what it does. You had loaded this data, right? R3, right? Now R3 is holding what? 0x01. Okay, let me show you here itself. 0x01. So it is written 0 0 0 0 0 0 0 1. Okay, now to count whether this number is 1 or 0, 1 or 0, how does the computer will know? Computer will not know anything. We should tell the computer that please, when you see 1, consider it as 1. When you see 0, consider it as 0. To do that operation, I am using one test operation here. Can you see here? Test. So this test is nothing but it is going to operate like an AND operation. Now one can ask me, instead of when you say that it is going to operate in AND operation, why did you write test? So I'll tell you the difference between TST, test and AND. AND is going to AND the two numbers and it is going to store the value in the first register. That means if I tell if R2 is holding 01, R3 is holding 02. Okay, if I do the AND operation, then R1 will store the updated answer. Here what I need to do, I don't want to do any AND operations. I don't want to update my value in the register. Rather I need to just check whether how many zeros are there, how many ones are there. To do that I require this test. So this is going to test for number of ones. Okay, now let me show you what it is. R3 with the 1. So this is going to test for number of ones here. Okay, see here, this is 0 1. This is going to test with the 1. Means what? I am telling R3 you AND it with the 1 only. Okay, I am taking with the 1 only. AND 0 0 0 0 0 0 0 0 1. So what is the output of this? Output is also 0 1 only. Output is also 0 1. That is why I am telling you this is going to test for number of ones here. Okay, if it is equal, then increment 0. If it is equal, okay, branch on equal. If it is equal, increment 0. Now it is not equal. Okay, because we have to check for all the bits here whether this is 1. Okay, so when it is 0, if the output is 0, no, see, if you do after AND operation, what is the output of this? Output of this is also same, this one. So 0 flag will not be set to 1. 0 flag will be set to 1 when the output is also 0. When the output is 0, 0 flag will be set to 1. As of now 0 flag is not set to 1. So branch on equal, this is not going to work. When this is not going to satisfy, it is not going to move to this particular label where you are incrementing R5. As I told you, R5 is going to hold the number of 0. R6 is hold to number of 1s. Now you got first 1, right? Then add R6 with 1. Yes, I am incrementing the counter of R6 to 1. Now what is the value of R6? 1. All of you can note it down. Okay, the value of R6 is now 1. Okay, branch on down. Okay, now go for this. Now shift it. Now what happens? Now you got the first number, right? This is over. This is over. Now shift right. When you shift right 0 1, how does it look? Shift right by how many bits? You see, shift right. Okay, logical shift right R3 by 1 bit. Okay, now check. See, this is 0 1, right? If you logical shift right with 1, now what happens? Now the next number will be what? Shift right. Okay, this number you have to shift towards right this time. That time this value will go back and it will store it as 0, and rest all the values are what, guys? Here it is 0 only. See, 0 0 0 0 0 0 0 0, every value. This happens when you logical shift right with the 1 bit. Now all the values of 0. Now what is the rightmost bit? 0. It is going to check 1 by 1 bit. Rightmost bit it check. Now what is the answer? You see 0. Okay. Now what happens? You see here. Subtract R1 with 1. That means you have decremented 1 bit counter. R1 was holding what here? 8. That means your first bit is over testing, right? Decrement it by 1. Okay, done. Right? R1. Now compare that R1 with 0. This is to check whether you are done with the, we are verified with all the bits here. No, we are not done. If it is not equal, please go to topic. Again repeat the same thing. Test it with the 0 1. Again test. Do the AND operation with 0 1. Now what happens? You see. What is the output we got? This is our output, right? 0 0 0 we got after logical shift, and it with the 0 1. Okay, 0 0 0 0 0 0 0 1. Okay, what is the output you get? 0 0 0 0 0 0 0 0 0 0. So you got the output as 0. That means 0 flag is set to 1. Now the computer, it is just like you are poking the computer telling, yes, now I got 0. Now I got 0. When you get 0, what you have to do? It is equal now. Now you look at here. It is equal. Branch on equal. Then increment 0. Go to this particular label here and add R5 with 1. Now R5 register is incremented by 1. That means the processor came to know that the count of 0, it got its first 0. Yes, now the counter of 0 incremented to 1, stored in R5. Again you go for the left shift right operation, so that you check with the second value. Since in 0 1 all the values are 0, okay, except the last value, so it will keep on iterating. Definitely once it is done with the first value, guys. Okay, I hope I will not repeat it again, because the same step it is going to perform. Same step it is going to perform till here. Okay, that means it has done with the first value. In the first value, how many zeros and how many ones it got? It has got only 1 ones and 7 zeros. Yes or no? Right? It has got only by the time of first iteration, guys, with the first value, I will tell you R5 is holding number of zeros. R5 is holding now 07 and R7, okay, and R6, sorry, R6 is holding the value now how much? 1. Okay, R5 is leading now, right? Number of zeros is 07 and number of ones is only 1. Okay, R5 is leading. Now what we need to do? Did we stop the program? No, we need to go further with the second number. Okay, let's move on. Now where we stopped? Yes, we stopped it here. Now we increment that R0 with 1. R0 is holding what? Address of the first one, right? First base. Increment by 1. Increment by 1, so that you can access the second 8-bit number. Incremented by 1 byte. 1 means 1 byte it is. You got my point, right? It is 1 byte. Okay, because we are working with the byte. If you are working with half word, put 2. If you are working with the DCD, then put 4. Okay, 32-bit numbers and all. Now it is only 8-bit number. No, increment with 1 byte. Done. Now we got the second number. Subtract R2 with 1. That means R2 become now 0 almost. Okay, why? Because we are done with the last number, right? If it is then compare, repeat checking. If it is not equal, then go up. Yes, now it is not equal. We have to go up. Yes, now check the same procedure for the second number. Again move R1 comma 8. R2 is 2, say 2 numbers, R1 comma 8. That means for the second number also there are 8 bits, right? 8 bits are there, right? This is 0F, say 8 bits are there. Now compare first value. Again load, okay, load the byte data from the R0 to the R3, and now it is 0F. Test it with the 01. Okay, test it. Let me show you one iteration. I hope the rest of the iterations you can imagine on your own. Okay, 01, 0 0 0 0 0, okay, 0 0 0 1. I'll put it in this way. Okay, 0 1. Yeah, now you see, and this operation, what you got? 0 1 only you get, correct? 0 1. Okay, 0F, if you AND it with the 0 1, you get 0 1, right? Now you got 1. When you get 1, what did I say? This is not equal. When this will become equal? When the 0 flag is set to 1. Now it is 0, the answer is not 0, so 0 flag will not. Add R6 with 1. What is the value we had in R6? You see, R6 was 1, now R6 became 2. Yes, okay, similarly do it. Okay, branch on down. Okay, branch on down, directly it will do left shift. Again subtract R1 with 1, compare R1 with 0. If it is not equal, go to top. Of course it is going to top. Okay, test for that. Now again you got 1. Now again R6 has incremented. Now R6 has become 3. Okay, next it becomes 4, and next it becomes 5. Once it becomes 5, now there is no more ones, because only 4 ones were there, right? Only 4 ones were there. Rest of the values are 0. So of course the R5 value will become 8, then it becomes 9, then it becomes A, then it becomes B. This is the final answer. 8 9 A B. Okay, So once it is done with all the iteration, definitely you can see here this condition will fail, and now you are going to load the address of ones in R0. Load the address of ones in R0. Why? Because we need to store finally the result in that ones and zero. That is nothing but the memory location. There I need to see my answer, not in the register. That's the reason I load it. Once I load it, I store the content of that R0 in R6, of course, because as I told you, R6 is a register which is going to hold the data of number of ones, okay, and store it, that R6, into content of R0. Done. Now once the memory location you have, what is the answer? 5. Similarly, you load the address of the 0 and put it in R0 and store that back into the R0, R5. Okay, R5 is going to store what? R5 is going to store the number of zeros. Store it in a R0. Okay, which is having the label is zeros here. So zeros will hold what? Zeros will hold 0B, and ones will hold 0.5. After that, stop. Done. Okay, stop. That means it is going to iterate in this line of code forever. Okay, so this is the end of the program, and you have to write it here. This is how it goes. Okay, now let us see the execution part of this program. Okay, do not forget to save the program if you have done any changes here. I hope you understood this program properly. Okay, now let me translate it, check for the errors, 0 errors and 0 warnings, build the program and click on the debug session. Once you click on the debug session, you can see the several windows like register window, disassembly window, text editor, command window and memory window. Now since if you go with the step by line execution, you can go it, but it will take 8 iterations for one number, so 2 numbers means 16 iterations it will take. I think it will take a long time to go for these options, so I'll directly execute it by pressing F5 here. Okay, now once I click on F5, you can see the value here. Can you see the values in R5 and R6 here, right? 0B, R5, what is R5 is holding? Holding number of ones. Once I told you already, it is 0B, 11 numbers. Okay, and R6 is holding number of ones, that is a 0, 5. Okay, so we are able to successfully execute this program, the number of ones and number of zeros. Okay, if you want to change the logic of the program in some other way, you can do that. Okay, try to decrease the lines of the code. It is always appreciable. Okay, anyways, I hope you all understood. If you have any queries regarding to this program, please drop your comments in the comment section below. Okay, thank you so much for watching.